today my talk will be on bridging computation and experimental predictions in materials machine learning model. So most of the work was done by my three group members, Chi Chen, who is my assistant project scientist, Yunxing Zhuo, who is my graduating grad student, and Ji Qi, also my grad student. So let me start by first putting some context about what I'm going to talk about today. So fundamentally, when we try to use machine learning in material science, essentially, for most of the time, what we want to get to is starting from a material, we put it into some machine learning model, and what we get out of the machine learning model is basically some ground truth, okay, plus some prediction error, right? Typically, the ground truth that we want to get to in the ideal case is the experimental value of what we measure, right? So inevitably, there are going to be errors in our prediction, and there are a few types of. We can classify that machine learning prediction error into several different categories, right? So the first kind of error is essentially what I call model errors, right? So this arises from our choice of the features and representation of our machine learning model. It also arises from the choice of the model itself. Now, there are also errors that arise from essentially our choice of the training data, okay? So there are limitations in terms of things like training data size. It is well known that in many instances, the data sizes in material science are relatively small compared to what is typically used in the data science field. There is also issues of data diversity, and in some cases, we just do not have a broad coverage of the data. Now, there are also methodological errors, and this is something that I want to focus on extensively today, in which case we know in a lot of machine learning models that are being trained for material science, we use DFT calculations to generate the data. And the main reason is because experimental data sets are much smaller than DFT generated data sets for the most part. But as we know, DFT is not perfect, right? And there's plenty of error there. And finally, of course, there's noise, and there's really not much we can do about that, right? Okay. Now, so in terms of the first type of error, which is the model error, this really part of it arises from essentially the choice of features and representations. Now, for machine learning models in material science, we actually in general, I would say that there are two major classes of features that people tend to use. There are elemental features such as the properties of the elements, such as the atomic number, group number, electronegativity, and so on and so forth. And these are very popular because, first of all, they are simple, they are readily available, they are easy to compute. But the problem is that if you just purely use these features, you cannot use the machine learning model to ascertain, you cannot train the machine learning model to ascertain differences between polymorphs. Now, my group extensively focused on the second type of feature, which is structural features, right? So, and depending on your use case, there are a few major classes of such structural features that people use today. I'm going to talk extensively about mathematical graphs in which you represent the materials as basically nodes and edges in a graph. I'm also going to talk about another type of structured representation, which is the local atomic environment or density. The good thing about structural features, of course, they can distinguish between polymorphs, but the problem is that they are more expensive and complex to compute, and they require the input structure, which ironically, you are going to require expensive DFT calculations to get to, right? And I'm going to talk about what we have tried to address this final problem how we have tried to address this final problem in our work. So the first broad category of machine learning models that I'm going to talk about are graph-based deep learning models. Okay, and these are we have used this primarily for property prediction models, right? Graphs are actually a very natural representation for materials. You can think of the atoms as nodes in the graph, and the edges and the bonds between them as essentially edges in the graph, right? In what we call materials graph networks, essentially what we do is that we represent the materials as a graph, and we allow information to flow between each of the elements in the graph, right? So we have a sequence of 3 steps. Okay, so we have vectors that are representing the atoms themselves, the edges, and there's also a vector representing the global state, which is basically the overall property of a material. Okay, and we then do a sequence of 3 updates, which we update the bonds, the vectors, the bond vectors with information from the atoms that are connected to that bond, as well as the global state. We then do atom updates, and then we do the state updates in a similar fashion, right? Now, because we don't really know what sort of functional relationship there is, or rather, we don't have an exact functional relationship between how the information should flow from these atoms to the bonds. So for these update functions, we have represented them using artificial neural networks. Okay. Now, so by stacking multiple of those blocks of sequential updates in a machine learning model, we can construct a model for predicting the properties of a material, starting from the input atomic positions and distances between atoms. And the nice thing about this materials graph network model is that you can actually stack it to generate models of arbitrary complexity and locality of interactions, right? So if the more blocks you have, basically you allow information to flow further and further away, and then you can model interactions that are much further away. So we have made all this implementation open source on GitHub. So if you're interested in the models that I talk about, you can actually download the code for yourself and test it out. So how do the materials graph network work? So in general, they work really well, right? So we have developed models using that framework for using crystals from the materials project. We can show that we can predict the formation energy to within about 28 MeV per atom using a data set of about 60,000 crystals. We can also predict things like the band gap to up to an error of about 0.33 eV. And we can also predict things like the bulk and shear modulus. And the data sets for these properties are in general much smaller. Now, how good are these? Is this performance enough, right? So this is always a question. Is this kind of error sufficient for us to use it for materials design and discovery? And the answer is actually surprisingly yes, right? So if you look at the formation energy error, it's about 28 MeV per atom. So there was this analysis that was done by Sun et al. Previously that showed that essentially if you look at all the crystals in the ICST, which we take it as a proxy that these materials are experimentally confirmed, you actually can show that about 80 to 90% of the crystal in the ICST is within about 70 to 100 MeV per atom, right? And with an error of about 28 MeV per atom, we are at least well within that threshold to determine whether a compound is stable or not, right? So this means that we can use this machine learning models for materials design purposes, at least for the formation energy, right? Now, the problem with all these structure-based model is that we have a major weakness, right? We need the input structure to be able to serve as the input to the model. And currently, there are basically 2 ways in which people use materials machine learning model. You usually, for example, if you want to generate a novel material, right? You will you may do an ionic substitution. Say you take SRTiO3. You say, okay, I'm going to replace that titanium with cobalt, right? Now, you can use composition-based model, in which case it's irrelevant. You don't actually need the structure at all. Or you have to do a really expensive DFT relaxation, and then you can use your more accurate structural-based machine learning model, right? So essentially, you're choosing between the devil and the deep blue sea, okay? And you either get more inaccurate results, or you get accurate results, but you have to do expensive DFT. So recently, what we have done is that we have coupled our magnet or materials graph network models together with a Bayesian optimization with symmetry relaxation process, or what we call Bowser, right? And Bowser is this creature from the Nintendo Super Mario games, right? So essentially what we do is that we use a Gaussian process and we treat the symmetry constraint lattice parameters and atomic positions as relaxation variables, right? And using this algorithm, we can basically say, well, we compute the energy of the structures by varying these constraint parameters, and then we find the variables that minimizes the energy predicted by our surrogate machine learning model. Now, given that our surrogate machine learning model is reasonably accurate, about 28 MeV per atom accurate, this relaxation process actually works reasonably well, right? Now, how can we see this, right? And the proof is in how does it improve our machine learning model, right? So what we have done is that we have taken we have generated a lot of hypothetical structures, technically not hypothetical in the sense that they are known, okay? Or rather they have already been computed by DFT. But what we have done is that we take structures in similar prototypes and we do ionic substitutions to generate hypothetical versions of the same structure, right? And if you do not relax the structures at all, basically what you see is that you get all these blue regions for the prediction of the formation energy, the bulk modulus, and the shear modulus. And you can see that the errors are very large, right? And this is not surprising because essentially you are not using the correct structure for your machine learning model. Now, however, if you relax it using this Bowser algorithm, what you see is that you get a significant improvement in your predicted formation energies or bulk modulus and shear modulus from your machine learning model, right? And this essentially shows that using this Bayesian optimization process, we can actually get at least structures that approximate the DFT relaxed structures to a good extent, such that we significantly improve our the predictions from the machine learning model. Okay, and finally, the yellow line is of course the DFT, and obviously that performs the best, but that requires you to do the expensive DFT calculations, right? Now, we can actually then, in other words, what we can do is that now that we have a way of getting relaxed structures without DFT, we can vastly expand our search space for potential new materials, and we can do that and by applying the Bowser algorithm to do on hypothetical structures. Okay, so what we have done is essentially we have constructed, we have taken about 5,000 ternary prototypes, and we have done elemental substitutions to generate unrelaxed about 400,000 unrelaxed candidates with of compounds, potential compounds containing moly, tungsten, osmium, and rhenium, and with the anion boron or carbon, to basically try to look for ultra incompressible hard materials, right? Now, using the Bowser algorithm, we can then get our relaxed candidates, and then we use our magnet machine learning models, which has already been pre-trained, to basically do a very, very rapid screening. So this screening takes literally less than a few hours, okay? To basically find the materials which have EHAL of less than 100 MeV per atom with high bulk and shear modulus, right? And finally, that actually brings us down to about 1,000 materials. And with those 1,000 materials, we now have a significantly reduced search space. We can then do DFT relaxation to actually get our final candidates, which is about 143, and we have chosen about 8 of them to try synthesis, right? And in collaboration with the group of Professor Tian Luo, my colleague at UCSD, he has actually managed to synthesize 2 of them, and these 2 are completely new compounds that have never been reported before, and they have indeed, what you can see on the right here is that they do, after using pulse echo measurements to measure their bulk and shear modulus as well as their hardness, we can show that they actually, the predictions from our Bayesian optimized structures with the machine learning model actually are very, very close to what is predicted, what was measured by in the experiments. Okay, so we have just submitted this work about a few months ago, and this work is actually on arXiv if you are interested to take a look. Okay, now so the second type of problem that we constraint that we we face in materials machine learning models, of course, data. And one of the key problems with materials data is that high value data, things like experimental measurements and accurate calculations tend to be scarce, right? So this is actually a distribution of the band gaps that we were able to get. You can see that we can get easily 50,000 band gaps from the materials project using the PBE functional. The number of HSE functional calculated band gaps are much smaller. The experimental band gaps are even smaller, right? And we all know that, for example, things like PBE actually performs terribly when we try to calculate the band gap, right? So the thing is that we take inspiration from how actually humans make decisions, right? So humans tend to make decisions by aggregating multiple sources of information, right? So for example, let's say if I want to know, come to a decision whether I should buy stock in Tesla, right? I will, of course, listen to the sage of Omaha, Warren Buffett himself. I'm going to maybe listen to some podcasts, for example, the Mad Money podcast. If I'm so inclined and I'm an expert, I would even look at the Tesla financial accounts. And of course, my Uncle Joe is going to have some opinion of his own that he will share with me, right? And once I aggregate those pieces of information, I'm actually going to then make my decision, or rather my prediction whether the Tesla stock is going to go up or down, right? Now, we can do this with materials data as well, right? So in our graph network models, we have this global state, okay? So by using this global state to encode fidelity information, fidelity meaning whether this particular data point is computed using PBE, GLB, HSE, or an experimental data point, we can create what is known as multi-fidelity graph networks, okay? So everything else remains the same, except that this global state is now a fidelity vector rather than fidelity embedding vector rather than representing the overall state of the material, right? And we can show that this actually performs extremely well, right? So if we construct single fidelity models, these are basically the MAEs in the band gap for from our single fidelity models for each of the data sets. And you can see that, for example, the smaller the data set, the higher your error tends to be, right? So PBE has the smallest error, is the least accurate, so you're making very accurate predictions about a very inaccurate band gap, okay? Things like the experimental and HSE band gaps are, data sets are much smaller, and you can actually see that the errors are higher, right? Now, by combining the PBE data together with the higher fidelity HSE and experimental band gaps, we can actually show that you can achieve about a 40 to 50% improvement in the high value band gap predictions, right? Now, a lot of people, whenever we show them this, a lot of people are like, well, this doesn't seem right? How can giving something bad data, which is the PBE data, improve the performance of prediction performance of good data? It seems like you're getting something for free, right? And this is not really true. So basically, the reason why the PBE data actually helps in the prediction of the high value band gap data, we can actually take a look at the latent structural features, and this is a TSME plot of it. And what we show is that with the large PBE data, even though the PBE data is underestimates the band gap, what it does is that it helps the structural features improve the underlying structural features, such that you can actually separate out the low band gap and high band gap materials, okay? And with this improved structural representation, that actually helps the machine learning model improve the predictions on the high value band gap predictions, okay? All right, recently we have actually also addressed another problem with graph-based deep learning models, okay? So this was actually work published by Anubhav Jain's group in LBNL, and basically this is the match bench dataset where they actually benchmark a lot of different properties using all the different types of machine learning models that have been reported in the literature. AutoMapMiner essentially is some ensemble-based machine learning model that automatically determines what's the best model for a purpose. The bottom line is this, right? So graph-based deep learning models, such as MagNet as well as the previous CGCNN models, tend to perform well only when you have very large data sets. So things like 10 to the power 4 data sets, right? While the AutoMapMiner actually tends to perform much better when you have smaller data sets, okay? So basically, what we want to do is to have our graph and edit tool. Okay, so what we have come up with is this atom sets framework, in which we still use our magnet models, but what we have done is that we have extracted the atomic vectors as well as the state vectors from the intermediate steps in our graph convolutional layers, right? And using these features, we can then use them to couple it with a standard multi-layer perceptron model to do predictions on different properties. So in other words, we have converted our materials graph network into sort of a multi-task model, right? And what we have shown is essentially that by doing so, we can actually significantly address a lot of the small data problems with graph-based deep learning, right? So what you see here is that a lot of the models utilizing the embedding vector, the atomic vectors and state vectors to construct this atom sets model, we can actually significantly improve the performance such that they are either better or at least on par with what you actually get from the ensemble models such as AutoMapMiner. Okay. All right. So can I clarify how much time do I have left, or? Five minutes. Okay, great. Okay, sure. So the second type of machine learning model that we work with is atomic local environment machine learning interatomic potentials, and this work was done in collaboration with Aidan Thompson, Gabor Sayani, George Baylor, as well as Alex Shapif, right? Now, I'm sure there have been many talks, so I'm not going to talk about this too much, but basically, essentially in machine learning, learning interatomic potentials, you have atomic descriptors which encode either the distances and angles between atoms, or you have some form of neighbor density, and then you couple these local environment fingerprints to various machine learning models, things like neural networks or kernel regression methods or linear regression methods, to basically generate your machine learning interatomic potential, right? So for example, neural networks together with these distances and angles give you your neural network potential. The gap is basically a kernel regression method together with your neighbor density. Snap is linear regression with the neighbor density, or rather the spectrum of the neighbor density, and so on and so forth, right? So I'm sure that previous talks have shown you that basically all variants of the machine learning model interatomic potentials tend to perform rather well. Okay. Now, what we want to show is that we have actually done an extensive study of the different types of machine learning interatomic potentials, and what we have found is that the model choice actually significantly affects the data requirements, and this is not surprising, right? So, for example, your neural network potential tends to require more data to actually converge to a certain test error in both the energies and forces. And this is not surprising, right? Because we know that neural networks tend to be a bit more data hungry than other models, right? Now, we also show that the feature type and model choice also affects the cost, complexity, and accuracy trade-off. So, for example, we have plotted, for example, the test error of different machine, the different machine learning interatomic potentials with against the computational cost of them, and based on the hyperparameters that are in each of the machine learning ML-IAPs. Okay, and what we found was that, for example, gap can reach the best accuracy, but in general, it tends to be the most expensive among the machine learning interatomic potentials by a factor of at least 10 to the power 2 to 10 to the power 3. The MTP, the moment tensor potential, and the neural network potential and QSNAP tends to lie fairly close to this, what we call the Pareto frontier, which provides an optimal balance between the computational cost and accuracy. Okay. Now, I actually want to show you in the final few minutes that we have applied this machine learning interatomic potentials to solve a real-world problem, which is predicting the ionic conductivity of lithium superionic conductors. Okay, so if you are in the battery field, you know that lithium superionic conductors are a very hot topic. People are looking for new superionic conductors to try to develop solid electrolytes for all solid-state batteries, right? Now, the classic way to predict the ionic conductivity of lithium superionic conductors is to do ab initio molecular dynamics. And unfortunately, almost nearly all the ab initio molecular dynamic calculations are wrong, right? And I can show you why, right? So this is actually a work from my group, right? And I purposely chose a work from my group because since I'm going to say that it is wrong, I might as well, I do not want to offend other people. Okay, so this was work that we had done in 2016, in which we did AIMD on this lithium superionic conductor. And because AIMD is so expensive, we can actually do it only at high temperatures, and then we extrapolate it down to 300K. And what happens is that in this extrapolation process, we actually get a predicted conductivity of about close to 60 millisiemens per centimeter. But if you look at all the experimental data that people have done, it is always 4 to 17 millisiemens per centimeter. In other words, we are off by at least a factor of 2, sometimes up to a factor of 10, right? And so what we did was that essentially we came up with a standardized way to construct a machine learning interatomic potential for lithium superionic conductors, in which we do AIMD simulations to generate training structures, and then finally we extract snapshots from it, and then we do static calculations to calculate the energies and forces. Now, one key thing to remember here is that we can now decouple the DFT functional that is used for the AIMD simulations themselves from the ones that is used for the DFT static calculations. And what we have done is that we use either PBE or the van der Waals OPTB88 functional to do our AIMD, and then we then do static calculations using either the PBE or the OPTB88 functional. And we generate a set of different moment tensor potentials using each of these methods, right? And what we show essentially is that the DFT errors are directly reproduced in the machine learning interatomic potentials. Okay, that's one. Okay, so in other words, the machine learning interatomic potential is doing exactly what they are supposed to do. They reproduce the DFT results, right? Now, the second thing that we found was that the choice of the method for calculating the training structure is actually less relevant than the one that is used for energy and force computation. So, for example, if you look at the results over here, you can see that the MTP, PBE, OPTB88, in other words, I use the PBE training structures but I use OPTB88 to calculate the energies and forces. The performance is almost exactly the same as the one that I used the OPTB88 to do the AIMD, and then followed by OPTB88 to calculate the energies and forces. Okay, so in other words, the training structure generation is just to sample a good range of local environments. So the functional use there is really not that relevant, right? So in other words, what you really want is to make sure you use the right functional for the energies and force calculation. And this actually has a significant impact. Okay, good. Yeah, so this actually has a significant impact on the MD simulations. Okay, so what we show here is this is the key result, right? So what we show was that using the ML-IAP for either using the PBE functional or the OPTB88, we see that with the OPTB88 functional, we actually get this transition between different Arrhenius regimes in our lithium superionic conductors. And this is fairly consistent between either oxide or chloride or sulfide superionic conductor. And because of this transition, the actual room temperature conductivities of these lithium superionic conductors are actually much lower than what you would have predicted if you have just taken the high temperature and then just extrapolated it down to room temperature. And in fact, all these room temperature ionic conductivities are much closer to what is in experiments. Okay, and we can actually, we also did some analysis which shows that the transitions are really due to change in the diffusion mechanism and dimensionality of diffusion in the various lithium superionic conductors at some temperature, okay, which is fairly low. All right, this is my concluding slide. So, what I've shown is that basically feature and model choices influence the cost complexity accuracy trade-off. We have showed this for magnet versus atom sets versus auto-map miner. Also with the machine learning interatomic potentials as well. We have shown that basically multi-fidelity and multitask models can help machine learning models learn from small high-quality data sets using large low-quality data sets. And finally, with the machine learning interatomic potential, we have shown that basically you can decouple the method that you use to generate the training structure with that used to calculate the energies and forces. This is actually very important because it means that hypothetically I can generate the energies and forces using a very expensive DFT method like HSE to get much more accurate answers, and then to train my machine learning in interatomic potential. Okay, and with that, I would like to thank everyone for your attention, and I want to acknowledge my group, especially Chichen, Yunxing, and T, as well as funding from Samsung, the ONR, as well as Nissan, and I'm happy to take questions. Thank you.